Hello everyone, my name is Vipin Mishra. I am the lead mentor at IMS Gate Academy and I welcome you all in this Gate Score Booster series. So I hope that you all are preparing very well and in the meanwhile you are enjoying our Gate Score Booster series as well. So yesterday I have taken a session on electrical machine, one of the most important core subject for all electrical engineering students, and today I am going to take a session on power electronics, another very conceptual and very important and scoring subject for all electrical students, right? So I am going to start the Gate Score Booster session on power electronics, and before that, right now it is the perfect time where you should be attempting more and more number of tests, where you should be practicing more and more number of PYQs, because you have already completed your syllabus and you might be doing revision. For that, we are offering you test series plus course, in which we are offering you 20% discount right now, and you can get all those features like test, PYQ booklet, doubt solving portal and score booster series as well. So do not miss this chance and you can buy this test series plus course of IMS Gate Academy. Now, starting from the very first chapter, which is power semiconductor devices. What are the important topics? Important topics are, you may get a question from power semiconductor devices. You may get a question from switching realization or switching power loss calculation and the commutation circuits. Right, I put commutation circuit in this chapter. Average weightage will be 1 to 2 marks. You may get one question or maybe two questions, right, related to semiconductor devices, which device we will use in what particular application, related to switch realization and their power loss calculation, related to commutation circuits, right. So this is what are the important topics, weightage of this chapter. Now, starting with the very first question. So this is our first question. See, so in this question what has been given to us is that a switch combination is as shown in the figure, will be operating as unidirectional, bidirectional, bipolar, unipolar, right. By unidirectional means it is handling current only in one direction. By bidirectional means that it can handle current in both the direction, right. Unipolar means it can block voltage of one polarity only. Bipolar means that it can block voltage of either of the polarity, right. And this is the switch given. So first of all we have to realize this switch, and then we will be in the stage where we can comment that what kind of switch is this. Okay, it is an MSQ kind of question. Okay, so let's start the discussion over this question. So we have been given a BJT and the diode is connected in a different way, right. So what is the switch realization of BJT? So if I have BJT, okay, while realizing the switch, you should be considering that what type of voltage the switch will block when it is in the off state and what kind of current the switch will carry when it is in the on state, right. So voltage during off state and the current during on state is what you have to see here. So if I talk about BJT, the switch realization of BJT is like this. It will block positive voltage and when it will be on, it will be carrying current in positive direction, means like this. Okay, good evening. Yes, good evening Matan. Now if I talk about diode, so if suppose I have diode connected in this way, right, if suppose this is P terminal, this is Q terminal, then the switch realization of diode will be like this. It will block the negative voltage and when you will apply the positive voltage, it will carry current in this direction, correct. So this is the switch realization of, the diode connected in this way. If suppose the diode is connected like this, okay, between these terminals, if suppose it is connected like this, then it will carry current in this direction, right. Then the switch realization of this kind of diode will be what? It will be able to block positive voltage and when it will be carrying current, it will be carrying current in negative direction, right. So individual switch realization of BJT, diode connected in this way, diode connected in this way, we know. Now we have to just do the series and parallel combination. So when the two things are connected in parallel, they share the common voltage and different current. When two things are connected in series, they carry the same current and different voltage. If you know this fact, then you can solve this very easily. So first of all, what we will do here, we will realize this in parts, right? How we will be realizing it? In parts. First of all, we will realize this particular combination, right? First of all, we will realize this particular combination. After that, we will realize this whole combination, right? The big box, and then we will try to realize this complete box. Okay. So first of all, realize this small box, right? So in a small box, what do we have? We have a BJT. We have a BJT and a diode connected in this way, right? And this is P terminal and this is Q terminal. Got it? So BJT and diodes are connected in parallel. So in parallel, you know what happens? In parallel, we take voltage to be same and current to be different, right? Same voltage and different current we have to take. Now have a look. Right now we are having this and this in parallel. You have to focus on BJT and this diode. These are their switch realization. Now from here you have to pick the same voltage. So what is the same voltage? It is carrying positive voltage. It is also carrying positive voltage. So common voltage will be positive voltage. Current we have to take both. So it is positive, it is negative current. We will take both the currents. So positive voltage and both type of current, right? So we have realized this much part of the switch. After that in this combination, we are having, after that in this combination we have connected a series diode in parallel as well, right? So just see, in this combination now we are adding a series diode as well, just like this. Okay. Now, so this much combination you have already realized. Now we have added a series diode as well. So with this and with the series diode, okay, and the diode is connected in this way. So this diode has this realization and the combination that you have already realized. Okay, so they are in series. So in series the current has to be common and voltage has to be both. Okay, so just see what is the common current between this switch. It is carrying positive current, it is also carrying positive current. So current that we will be taking is the positive current, right? And voltage can be different because it is series connection. So here we have positive voltage and here we have negative voltage. So we will take both the voltages, correct? So this is a combination of this particular switch. Now after realizing this, we have added another diode. Okay, so let me connect another diode here. So first of all I will realize this combination of switch, okay, that we have already done. Now it is a time to add one more diode here. Okay, so what I will do, we have added one more diode in this combination, correct? So up till this you have realized. Now you have diode like this. Okay, this diode means we have this combination. Okay, so we have to compare this characteristic with already done characteristic. So they are connected in parallel. In parallel what happens? In parallel we will take same voltage but different current, right? So what is the same voltage, common voltage between this characteristic and this characteristic? It is having positive voltage, it is also having positive voltage which is common. So we will take positive voltage. Okay, current we can take both. Here we have positive current, okay, and here we have negative current. So we have to take both the currents because it is parallel combination. So we will take it like this. Okay, now this is the switch realization that we have obtained. Got it? So how we have done? Just series parallel combination, and first of all we have done individual switch realizations, right? So what kind of characteristic we are getting for this combination of switch? We are getting something like this, Vi minus I and minus V. We are getting something like this. Okay, so it can carry current in both direction. So it is bidirectional, right? and it is able to block voltage of only one polarity, which is positive. So it is unipolar, right? So it is unipolar and bidirectional. Got it? It's not only bipolar. Medha, why you are saying bipolar? Yes, it is like MOSFET. So if the MOSFET is not available, you can use this combination, right? If the switching frequency, high switching frequency is not a concern for us, we can use this combination of switch, right? So this is a very good question, right? Normally they have asked questions like that, what is going to be the switch realization? They may ask question in this way as well, asking about bidirectional, unidirectional, unipolar and bipolar, right? So I hope that this question is clear to everyone, right? Very good. Correct. So this was the first question. Now have a look over this question. This is the second question that we have. So the circuit shown in figure below has VCC equals 70 volt, inductor value equals 180 millihenry, resistance is 10 ohm, T1. So this is the switching sequence given, where T1 is 5 millisecond and total time is 100 microsecond. Then the peak value of energy stored in the inductor in joules will be what? Okay. What will be the value of peak energy that this inductor will store? Okay. This is what we have to calculate, right? So just see. So during T1 or at T1, what will happen? At T1, BJT is on, right? Because we have given the base signal. So once you will give the base signal, the BJT will be on and your circuit will be like this. Okay, whatever we know, we are just going to apply that concept. So when BJT is on, it will be acting as a closed switch, right? So this is your inductor. Now when current, this is VCC. So when inductor will store energy, current will start increasing across it and the inductor voltage polarity will be like this. Now because of this polarity of the inductor, what will happen to the diode? The diode will be off, right? The diode will be off. So this is the circuit, correct? This is going to be the circuit that we will be having. Now whatever energy it will store, same energy it will release. So if you will calculate energy for one part, it is sufficient, and we only know T1 time, so that is sufficient. So calculate energy. So when you have to calculate energy stored will be half Li square. So we need to calculate this current I. How you will calculate this current I? Okay. So if you will see, the active part of the circuit is only this one. The active part of the circuit is only this part of the circuit, right? Now in this circuit, what you can see, that when you will apply KVL, you will get VCC minus VL equal to 0, or you will get VL equals VCC. VL you will write LDIL by dt equals to VCC, or IL you can write 1 by L integral T1 VCC dt, or it will be 1 by L or VCC by L into T1, right? Now how much is VCC? 70. Okay. And how much is L? The L value is given 180 millihenry. And how much is T? T1 is given 5 milliseconds, right? So from here, once you will calculate this IL, how much it is going to come? How much will be the value of IL? So the IL value will be 1.94 amperes, right? Now come back here and put the values. So L is 180 millihenry, right? L is 180 millihenry, and the current that you have calculated is 1.94 square. So when you will solve this equation, you will be getting 0.34 joules as the energy, correct? So this is how you will solve this question. You may consider this as a analog problem, you may consider this as a network problem. I consider this to be a power electronic problem, right? So is it a good problem? Yes, right? So this is how you can calculate the peak value of energy stored in the inductor in joules. We have to calculate energy stored, okay? So inductor will be storing energy during the time t1 when the switch will be on, means the BJT will be on. Got it? So is that question clear, that how you will be proceeding for this particular question? At the time t1 BJT will be on, so turn on the BJT. Now when inductor current will start increasing, it will start storing energy, then the polarity of inductor will be like this. Because of this polarity, diode will be off, so this part of the circuit is inactive. Now the active part of the circuit is this. When you will apply KVL, you will be able to calculate IL. After calculating IL, energy you know is half Li square, and you will get it like this. So is that part of question is clear? Tell me, is that question clear to everyone? I hope that you are also getting the same answer, right? Okay, so it's a very good question. Okay, you can expect this question in exam. Now after that, moving towards the next question. So this is our third question. Okay, and what is given in this question? The voltage across and current through the MOSFET during turn on transition are shown below. So this is the voltage and current transition that we have, right? If the switching frequency is 82.5 kilohertz, we need to write this data. Switching frequency is 82.5 kilohertz. Right? The power loss in the MOSFET will be, we have to calculate that how much is the power loss, right? So we have a direct formula, okay? We can calculate energy loss during on time and off time, and that formula is energy loss during on time is VCC ICC upon 6 into T on. Energy loss during the off time is VCC ICC upon 6 into T off. But that formula we will apply for a particular characteristic, okay? If you have covered that particular topic in your classes, you might be knowing that, but that is not a perfect match, okay? So we will use the process. We have to calculate energy, power, and power is energy over time, right? So we need to calculate the energy first of all. So how we will calculate energy, okay? So if I have to calculate energy, so energy is what? Energy is instantaneous power. When it is integrated will give you energy, and instantaneous power is Vt into It dt. This is how you will calculate energy, right? Now this characteristic has two parts. One is for 5 microsecond, another is for 10 microsecond. So we can break this energy into two parts. For 5 microseconds, right? If I break it for 5 microseconds, just see what is my voltage. Let me write it once. Voltage into current. Then I have another part for 10 microseconds, right? And at that time again I will write it Vt into It dt. Got it? Now for the first 5 microsecond you can see voltage is constant, so you can take voltage out. Then it will be It dt. Then for the second part of the circuit you can see current is constant, so you can take current out and it will be Vt dt. Okay. Now this indicates the area under the current curve. Okay, this indicates the area under the voltage curve. So we have to calculate the areas. So what will be the areas? Okay, so just see, I am talking about this area. We have to calculate this area under the current curve, and we have to calculate this area under the voltage curve. So we have to calculate these areas. So if we focus on the first part, Vt, which is constant, so Vt is how much? 30, right? Into what will be the area of this curve? This is a triangle, so it will be half into height, height is 8 into width is 5 microseconds, right, plus IT. Here IT is constant, so which is 8, right, and area under the voltage curve, so it will be half into height is 30 and the width which is 10 microseconds. So in this way you will calculate the energy, right, and the total energy coming after this calculation when you will solve it. So I have calculated and the energy is 1800 into 10 to the power minus 6, right. This is the energy that I am getting. Once you will calculate the energy, then how you will calculate power? So power will be energy over time or energy into the frequency. 1 by T is F, right, energy into frequency. So energy you have already calculated, frequency is given to you. So 1800 into 10 to the power minus 6 is the energy and frequency is 82.5 into kilohertz, 10 to the power 3. So when you will calculate, the power will be 148.5 watts. Got it? 148.5 watts. This is how you will be calculating the power. Power is energy over time. So first of all you will have to calculate energy, and energy will be calculated in this way, right. It might be for MOSFET, it might be for BJT, it might be for any switch, and they will give the switch characteristic. You will be asked to calculate the same thing again, okay. So from a long time we have not seen questions like this in GATE exam. So this year you may get a question like this, okay, and that is why I have taken this question to just refresh these concepts of yours, right. So this year I am expecting a question from this kind of characteristic. Everybody is getting the same answer, 148.5 if you are calculating. So I hope that this question and its solution is clear to everyone. Is it? Right. Now after this question, now we have a question from current commutation circuit. Just see this question. So what has been given in this question is the current commutation circuit is shown in the figure below. So we have the current commutation circuit. If the capacitor and inductor values are 20 microfarad, okay, so this is the capacitor which is 20 microfarad and this is the inductor which is 7.5 microhenry. The circuit turn off time for SCR will be what? We have to calculate that how much will be the circuit turn off time, right. This is current commutation circuit. So how to calculate circuit turn off time for current commutation circuit? Anybody who knows the formula can type. What is the formula for circuit commutation time? When the main thyristor will be off, after that for what time the reverse voltage is still applied across the circuit, that is what is known as the circuit turn off time, and we have to calculate that time, okay. Circuit turn off time means TCM. So what is TCM? Anybody who knows the formula for TCM? You may type it in the chat box. I just want to see whether you have the formula or not. TCM, isn't it C VR over I naught, right? Very good. Circuit mania. What is your actual name? Circuit mania. CVR of I, CVR upon I. Very good. That's right. Okay. CVR upon I naught. Now we have to calculate VR, and what is VR? VR is actually the capacitor voltage. The capacitor voltage at the time when we have applied the reverse voltage, okay. So it will be what? It will be Vs cos sine inverse I naught over IP, isn't it? Is that correct? Right? Chetan, very good Chetan, you have very good name, Circuit Mania as well. Dharmendra is getting 19.2 microsecond, is it correct? No Dharmendra, I am having different answer, right? Gautam Desai, sir, I don't know commutation circuit concept, but it is important for GATE. Please tell me how to solve question if question comes from this topic. That is what I'm doing here, okay? Gautam, you can take reference of these questions, right? So circuit turn off time will be CVR upon I naught, okay? And how to calculate that VR? That VR is the reverse voltage applied by the capacitor, or it will be capacitor voltage, and it is calculated like Vs cos sine inverse I naught upon IP, right? Now what is this I naught and IP? I naught is given to you, and what will be IP? So if I calculate the current IP, okay, so IP, you know, it is equals to Vs under root C over L, right? What is Vs? Is 220 volt, correct? Vs is 220 volt. And what is the value of C and L? The C value is given 20 microfarad. So 20 microfarad upon L value is given 7.5 microhenry. Right. So when you will solve it, you will get the IP value as 358.6. Right. So the IP value will be 358.6. 358.6 amperes, and I naught is already given, which is 140. So now come back here and just put all those things. So Vs is how much? Vs is 220 volt. So 220 cos sine inverse I naught, which is 140, upon IP is 358.6 amperes. Okay. Now when you will solve it, you will get the VR value, the capacitor voltage, which will be acting as a reverse voltage, and I am getting it 202.5 volts. Okay. So now the job is done. We have to calculate circuit turn off time. So it will be C VR upon I naught here. Okay. So what is the value of C? 20 microfarad. VR you have calculated 202.5 divided by I naught, which is 140. Okay, so when you will solve it, you will get 28.93 microseconds. 28.93 microseconds, right? So how many of you are getting exactly the same answer? How many of you are getting exactly the same answer? Dharmendra, can you just re-verify? Chetan is also getting 28.94. Harini is getting 28.8, which is very much close to this. Okay, so that's correct, right? Dharmendra, you can re-verify your answer. Maybe you might have mistaken somewhere. Correct. So just see, in this way you have prepared the formula of how to calculate VR, how to calculate circuit turn off time. Apart from that, very good Niharika, apart from that, they may ask you that what is the maximum value of current across main thyristor, what is the maximum value of current across the auxiliary thyristor. Okay, so you may prepare those formulas as well. So ITA peak is equal to IP, or it is equals to Vs under root C by L, right? And what is ITM peak? Can anybody tell me what is ITM peak? The peak value of current across the main thyristor. Peak value of current across the main thyristor. When auxiliary thyristor will be on, okay, the current will be flowing in this circuit. So it is IC current. The peak value of IC will be ITA. Okay, and when main thyristor will be on, at that time the diode was off. Okay, when this thyristor is on because of this polarity. So if I have to calculate that what is going to be the ITM peak, okay, so the peak value of ITM will be I naught. Got it? So these are the another important formula which you can expect, you can get a question from these topics. Okay, so either they will ask you for the circuit turn of time, or they will ask you to calculate the reverse voltage capacitor that has applied, what is the value of that. You may be asked to calculate ITA peak, you may be asked to calculate ITM peak. Okay, Nitya, how are you, Nitya? Got it? So just see. So Gautam, you are saying you are not too much good in these topics. So just see, through this question I told you all the important formulas. You can practice those. You will not get anything beyond them. Got it? So in this way we will solve this question, and I can see that you all are getting same answer. Okay. Now after this question we have another question, and this question is from voltage commutation circuit. Okay. Now what we have to calculate here, a voltage commutated chopper operating at 1 kilohertz is used to control the speed of a DC motor. Okay, the load is a DC motor. Okay, so we have supply, we have thyristor, and this is DC motor, so it is controlling the speed of DC motor, right. We have connected this part of the circuit which is acting as a commutation circuit, right. So this part of the circuit is basically the commutation circuit that we are using to turn off the main thyristor. The output current is assumed to be 10 ampere. So we have the value of I naught. I naught is 10 ampere and it is constant. The average voltage received by the motor will be, what will be the average voltage here is what we have to calculate. Okay, what is going to be the average voltage is what we have to calculate here. Okay, so those who have covered this topic, they know that how to calculate this average voltage. Okay, if you don't know, then also I am telling you. So average voltage, so when you have completed this topic, you might be getting average voltage as, just see, when TA is on, okay, then average voltage is, so let me call this on time. Okay, so this is T on, means the time for which TA is on, sorry, TM is on. So when TM is on, source and load are connected, output voltage will be equal to the input voltage, right, means it will be equals to Vs. This is Vs, correct. So output voltage is equals to Vs during the time of TM. T on means TM was on, right. Now when TM will be off, immediately TA will be on. Okay, when TA is on, the polarity that is favorable to it will be this polarity. Got it? Now with this polarity, if you will apply KVL here, okay, if you will apply KVL into this part of the circuit, just see what you will be getting, Vs, and this voltage will also be Vs. So Vs plus Vs minus V naught. So V naught will be 2 Vs. Okay. So during the time when TA is on, the initial voltage will be 2 Vs. Okay. Now when TA will be off, at that time what could have been the polarity? When TA will be off, at that time the polarity that will turn it off will be like this. Okay, this will be plus, this will be minus. Got it? Then TA will be off. Now when you will apply KVL, so Vs minus Vs, 0 minus V naught. So V naught will be 0. So that means when TA will be off, at that time the voltage is getting equal to 0. Correct? The voltage is getting equal to 0. So this is the time which will be 2 times TCM. Okay, this time is known as 2 times TCM. This is the time when TA will be off. It will be on or it will be off as well, right? So this is the time where TA is on, and we will turn off TA at this particular time. correct? It is the time where TA is on and TM is off, correct, and TM is already on at this time. So in summary, you can just write this in this way, okay? Those who have covered this topic, they already know this waveform. So this is the waveform of output voltage, correct, which is V naught, right? Now if I have to calculate that what is going to be the average voltage, okay, if I have to calculate that what is going to be the average voltage, then average voltage V naught average will be, okay, just see, this will be the total time from here to here. The time that you have is the total time, right? So V naught average will be 1 upon T, okay. How to calculate average voltage? 1 upon T, within the time period you will integrate V naught dt, okay, and this is nothing but the area. So we have to calculate this area. So this area will be 1 upon T. Now this area is, just see, we have two areas here. One is this square area and one is this triangle area, okay. So what is the square area? Square area will be Vs into T on, and what will be the triangle area? It will be half into, the height is 2 Vs and the width is 2 TCM. Got it? This will be the final formula that how you will be calculating the average voltage. Now we need the value of T on, we need the value of TCM to calculate all those things, okay. So first of all, calculate these two things. What is T on and what is TCM, right? So T on and TCM, we have to first of all calculate these two things. So if I am going to calculate T on and TCM first, so just see, we know the formula of T on and TCM in this case. So T on will be pi under root L C, right? Or just put the value pi, what is L and C? So I think the space is not sufficient, let me use the lower half. Okay, so let me use this half to calculate these two things. So T on will be pi under root LC, pi 3.14 under root L and C. What is the L value? 50 microhenry. What is the C value? 1 microfarad, correct. When you will calculate this, then it will come, the T on value is 22.2 microseconds. 22.2 microseconds, right? Then when you will calculate TCM, then how to calculate TCM? Same. What formula we have used in the last case? CVR upon I naught. Here in this case it will be C Vs over I naught, okay. Reverse voltage is complete Vs. So what is the value of C? 1 microfarad. What is the value of Vs? 300 upon I naught. I naught is 10 ampere. Correct. So what you will get from here? You will get 30 microseconds, right? So in this way you can calculate TCM and T on. I hope that it is clear, right? In this way you can calculate TCM and T on, right? Once you have calculated these values, just put it here. 1 upon T, okay. So just see, T will be 1 upon F, and what is F? Or simply we can write 1 by T to be F, okay, and F is given 1 kilohertz. So what I can write here is 1 kilohertz into Vs I can take out, right? So the things will become easy. So Vs I can take out, Vs is 300 volt. Then I have to write T on, which is 22.2 microseconds, right? Then this 2 and 2 I can cancel, okay, and I have to write 2 TCM. So 2 times TCM is 30 microseconds, correct. Now when you will solve this equation, the output voltage that you will be getting is 24.66 volt, 24.66 volt, right. How many of you are getting this? 24.66, okay. Remove this commutation circuit, then what kind of circuit is this? Isn't it similar to a buck converter? So in buck converter what will happen? You will get less voltage as compared to the input voltage. Are we getting this? Yes, right. So in this way you have to calculate the average voltage, okay. Now this is the most complex thing that you can be asked to calculate from voltage commutation circuit. Last time they asked a question from voltage commutation circuit, they have connected capacitor instead of this place, they have connected at this place. That does not matter, that does not create any difference, and they just have asked for the circuit turn off time. So TCM only you have to calculate, which is CVS upon I naught. So the very simple question that they have asked, right. This is the most complicated part that they can ask. So you have learned to how to calculate average voltage, you have learned to calculate on time of main thyristor, or the time for which the main thyristor was on, or the minimum time for which it can be turn on, turn off. So this is T on, right. You have seen that how to calculate circuit turn off time. Apart from that, if suppose they will ask you that what is the peak value of current across the main thyristor, okay, and they may ask you that what is going to be the peak value of current across the auxiliary thyristor. So ITM peak is I naught plus IP, okay, or I naught plus Vs under root C by L. Remember this formula, you may be asked to calculate this, or otherwise they will ask you that what is going to be the ITA peak. So peak value of current across ITA is, or TA is I naught, okay. So whatever can be asked from voltage commutator circuit, all the important formulas are written in front of you, okay. Prepare these formula and surely you will get a question. If suppose you will get a question from voltage commutation, it might be only from this topic. Last year 24, they just asked to calculate circuit turn off time. So you only were required to use CVS over I naught. Vs is given to you, C is given to you, I naught is given. TCM you could have calculated very easily, right. So in this way you have revised voltage commutation circuit and you have solved this question as well, right. Everything is clear, okay. Those who do not know anything about, who does not know anything about this circuit, I think now you are very well prepared about these topics. Got it? So is that question and various things are clear? I hope you also are getting same answer, those who have solved. Anybody getting the same answer? Reply in the chat box. Right. Now after that, moving towards the next chapter, which is a very important chapter from power electronics, and which is DC to DC converter. It has a capability that it can give you 3 to 4 marks of question in the GATE exam. 3 to 4 marks, mind my words. Important topics: buck converter, boost converter, buck boost converter. The best thing is that if you have understood the operation of one converter, you have to follow the same legacy in all other converters, only the circuit will change, right. So can you people tell me that in buck converter what is the position of inductor, at the source side or at the load side? What is the position of inductor in buck converter, source or load? What is the position of inductor in buck converter, source side or the load side? Load side, very good. And in case if the inductor is present on the source side, it will be boost converter, and if the inductor is common between the source and load, then it will be buck boost converter. This is how you can identify which type of converter we have. Okay. Now starting from the first question, so this is the first question that I have, and I want you people to answer this question. I just want to see that how much comfortable you are in this topic, because what I told you, this is the most important chapter in power electronics, which has a capability of giving 3 to 4 marks of questions, right? The very first question is, we have been given a step down or buck converter which is being fed from 220 volt DC, is operating on a chopper frequency of 2 kilohertz and the duty cycle is 0.4. What is going to be the RMS inductor current, right? We have to calculate that what is going to be inductor current RMS value. Okay. Now your fundamental skills of calculating RMS will be utilized here. So if I have to draw the RMS current waveform, if I have to draw the inductor current waveform, so how is the shape of inductor current waveform? Whatever converter you talk about, buck boost, the inductor current waveform is having this particular shape, right? For continuous conduction, it will be increasing from minimum to maximum value during the on time of the switch, then it might be decreasing from maximum to minimum value during the off time of the switch, right? And then this will be the average value, correct? So this is the inductor current waveform, where this is the minimum value, this is the maximum value, right? And this will be the average inductor current, right? And we call this height as, and this height as, this is what? This is peak to peak ripple current delta IL, and what is this? Delta IL by 2. Okay. So this is the inductor current waveform, right? Now what is the shape of this waveform? A shifted triangular wave. So if you have to calculate the RMS value of a shifted triangular wave, then if you are my student, I normally teach this thing first of all in class, okay, before actually moving into the chapter. So it will be IL average square the shifting amount plus above the shifting, okay, how much is the amplitude? Delta IL by 2, okay. Then for a triangular waveform, what is the RMS value? Amplitude by root 3. So above the base, the amplitude is delta IL by 2 by root 3, and we will do a square of it, correct? So this is the formula of calculation of RMS value of this kind of waveform, right? For this kind of waveform. Now what you can see, that we require to calculate IL average, we require to calculate delta IL by 2, and then we will get this answer easily. So what is going to be the IL average? So this is boost converter. In boost converter, IL average is I naught upon R. Whether we have been given I naught? No. So I naught can be written V naught by R. V naught is given? No. V naught is dVs over R, right? Now we have been given the values. So D is 0.4, Vs is 220 divided by the resistance, which is 20. So how much we will get as IL average? So IL average that I am getting is 4.4 amperes. It is 4.4 amperes, right? After that, delta IL, okay, delta IL by 2. So delta IL is D 1 minus D Vs over FL, right? D1 minus D Vs over FL. This is the value of delta IL, correct? Now just put all the values. So D 0.4, 1 minus D 0.6, Vs 220 divided by 2 into the frequency is 2 kilohertz and the inductor value 10 millihenry, right? So when you will solve it, you will get delta IL as delta IL by 2 as 1.32. Okay, this is going to be 1.32. So just see, we have used the formulas of individual currents and we have calculated their values. Now just put it here. So if you will write these values here, IL average is 4.4. So 4.4 is square plus delta IL by 2 is 1.32 divided by root 3 is square. So when you will solve it, right, then what answer I am having is 5.16 ampere. 5.16 ampere. Okay, Meghanathan is getting I naught as 4.4. Very good. Good to see you, Meghanathan. And Harini, what is 2.78? What is the final answer? Is the final answer 5.16 correct? Cross check, guys. My answer might be wrong. Okay, so I'm just asking you the correct answer. Are you getting the same answer? 4.46. Any other answers? Anybody getting 5.16? Anybody getting 5.16? Meghanathan, what is the final answer? 4.46. Okay, then maybe I have done a wrong calculation. So 4.46 will be the right answer. Correct? Whether IL average, delta IL by 2 you are getting same? Very good. Yes, so 4.46 is the right answer, right? I might have done wrong calculation. So I have written this. Okay. Sir, my network got interrupted. Could you please just brief once? In this question, we have calculated IL RMS. Okay. So inductor current waveform is like this, where this is IL average and this peak is delta IL by 2. So whenever you have such a shifted triangular waveform, how to calculate the RMS value? It will be, what is the base? IL average square plus what is the height above the base? Delta IL by 2, that is the peak, divided by root 3 square. Okay. So this is what you have to use. Then individual formulas of IL average and delta IL by 2 is this. Calculate everything, put it finally, you will get 4.46 as answer, right? So they have never asked to calculate IL RMS. I am expecting that this time they may ask to calculate it. Okay. At that time, if you don't know how to calculate RMS value of such a shifted waveform, you cannot solve this problem even if you know all the formulas, right? So I hope that it is clear, and what I can see that everybody is getting right answer. So very good. Now see this question. This is from boost converter. A boost converter produces 40 volt from 20 volt. Okay, it produces 40 volt from 20 volt. Produces 40 volt means output is 40 volt, from 20 volt means input is 20 volt. Across 8 ohm resistor, so resistance value is 8 ohm. The output voltage ripple must not exceed 0.5%. Delta V naught is 0.5%, so that the converter operates at the boundary of continuous conduction, right? It is operating at the boundary of continuous conduction. The RMS inductor current is, okay, and the switching frequency is given 100 kilohertz, right? We have to calculate the RMS inductor current. So you know that this waveform is going to be the same waveform whether it is buck converter, boost converter, buck boost converter. So the process of calculation of IL RMS is going to remain the same, right? That means we have to use the same formula. Okay. So what is IL RMS? if you want to calculate IL RMS, then it will be IL average square plus delta IL by 2 divided by root 3 square. Correct? We need not to draw the waveform again and calculate the formula. So, the formula is going to remain the same because the shape of the current is going to remain the same in all kind of converters, right, whether it is buck boost or buck boost. Now, again we have to calculate these different currents delta. So, first of all we will calculate IL average. Okay. So, what kind of converter we have? We have boost converter. In boost converter or in buck boost converter, the average inductor current has the same formula. And what is that formula? That formula is I naught upon 1 minus D. Correct? Do we have the value of I naught? No. So, we can calculate it by V naught by R upon 1 minus D. Do we have the value of V naught and R? Yes, we have. So, we can write it V naught by R upon 1 minus D. So, what is V naught? V naught is 40. So, 40 divided by 8 divided by 1 minus D. Whether D is given to us? No. So, first of all we have to calculate D. Okay. How we can calculate D? So, let me calculate first of all the value of D. Okay. So, for D calculation you can apply V naught equals to Vs over 1 minus D, or 1 minus D will be Vs over V naught. Vs is 20, V naught is 40. So, you will get it 1 by 2, or D will also be 1 by 2, right. So, we have calculated D. Now, if you will put 1 by D, which is 1 by 2 here, then you will get IL average. And how much is IL average coming? 10 ampere. Correct. Then we have to calculate delta IL. Okay. So, delta IL formula in case of boost and buck boost converter, both it is same, dVs upon F into L, right. If we are calculating delta IL by 2, we have to write an additional 2 here. Now, whether we have D? Yes, we have 1 by 2, Vs is 20 upon 2 into the frequency is 100 kilohertz. Inductor value, oh, do we have inductor value? Inductor value is also not given. How to calculate inductor value? Okay. So, if you want to calculate inductor value, then how you will be calculating it? Okay. So, just see, for inductor value, okay, for boost converter, what is the inductor value? Anybody who can tell me? Converter is operating at the boundary of continuous and discontinuous conduction, right. So, we can calculate the inductor value, critical inductance, which will be D 1 minus D square R by 2F. How I am getting this formula? We have different formula for different converter. If suppose you forget, then how to calculate it? What is the condition for calculation of this? I minimum is equals to 0, or IL average should be equals to delta IL by 2. You have to just simply apply this condition, and anytime, anywhere you can calculate this formula, right. Now, what is the value of D? In our case, it is 1 by 2. 1 minus D will be 1 by 2 square into resistance is 8 upon 2, frequency is 100 kilohertz. Okay. So, once you will do this calculation, you will get the value of L, and that I am getting as 5 micro Henry. Got it? In case of boost converter, this is the formula. In case of buck converter, what is the critical inductance formula? It is 1 minus D R by 2F. Is that correct? Tell me. 1 minus D R by 2F. Is this the formula? Suppose you forget this formula, okay, then let me just calculate it. Okay, in one such case I will calculate and then we will see whether this is a correct formula. Let us verify. Okay, if suppose we forget, different formulas are there. IL average is how much? I naught upon 1 minus D. Delta IL is dVs over 2F and L will become LC, right? Now I naught we can write V naught by R, and V naught we can write Vs over 1 minus D square into R dVs over 2F LC, correct? Now from here you can see Vs and Vs will be cancelled. Okay, so what we will be getting, LC is D 1 minus D square into R by 2F. Okay, so is that formula that we have applied is correct? Same we are getting from here, right? Okay, so if this is a buck converter, then what would have been the formula? LC will be 1 minus D R by 2F, right? If it is buck boost converter, then what would have been the formula? For buck boost converter, it will be 1 minus D square R by 2F. What we have to do? We have to apply the same condition, correct? Right? Okay, both are 10. What is 10? I am not getting what you are saying, sir. Directly we can take from IL average. Okay, so by the way, if you have calculated LC, are you getting 5 microhenry? Okay, once you are getting 5 microhenry, you can write it here. Okay, so 5 microhenry. Okay, then you will get delta IL by 2 equals to 10 ampere. Acha, that you are saying both are 10. Okay, right? I got it. So those who are not having practice of formula, just see, this is how you can practice the formulas. Okay, I am telling the formulas used as well. So in this way we have calculated D IL average delta IL by 2. Okay, now come back here and put the values and get your answer which you require to calculate. So IL average 10, delta IL by 2 10 by root 3 square. Finally answer will be 11.55 ampere, correct? The values of delta, if we can take from IL average only, the values of delta if we can take from IL average only. Okay, but whether we have been given Imax, Imin, okay, that you have to think. There might be different approach. Okay, you can solve one problem with different approach. This is one such method which I have used. Okay, Bindu. So 11.54. Very good, Harani. You are getting the same answer. So is that problem clear to everyone? Okay. In this way, I have used so many problems, and how to just approach for those problems, I think you might have realized. Got it? Now, this is going to be the formula for IL average for all kind of converter. Every time we will need IL average and delta IL by 2. So IL average is equals to I naught in case of buck converter. It is equals to I naught upon 1 minus D in case of boost and buck boost both converters. Delta IL is D1 minus D Vs over FL in buck converter. It is D Vs upon FL in both boost and buck boost converter. Got it? Then you should know the individual formulas for output voltage as well, and that's it, right? And then we have discussed the critical inductance formulas and how to get that if suppose you forget. Okay, so in this way we have calculated RMS value of current in case of first buck converter and then boost converter, right? The purpose was to get you revise all the formulas as well and the approach that we are using, right? Now see this question, question number 8. The switch shown in figure is ideal. Very good. The value of duty ratio so that converter operates in the boundary of continuous conduction, right? Ripple doesn't matter. Chetan, will you elaborate your question? Ripple doesn't matter. Ripples are there, that's why you are doing that much calculation, isn't it? If suppose there is no ripple, there is no objective of inductor and capacitor, you are using inductor and capacitor to reduce the ripples, and that's why we are having that many number of calculation. If suppose the fixed DC is easily converted into variable DC, we need not to calculate, and then the output is pure DC, current will be simply voltage divided by R without any ripple, right? Because the ripples are there, that's why we are using inductor and capacitor to minimize them. Last question. Last question, ripple does not matter. Acha, this data that they have given, this is of no use, okay? This is of no use, we have not utilized this. This is the output voltage ripple given, and we have not utilized the output voltage ripple formula. Simple current calculation you will do and you will get everything, right? We will not utilize that data, okay? We have not used that output voltage formula, right? Now focus on this question. So what we have to calculate here is the value of duty ratio so that the converter operates at the boundary of discontinuous conduction, correct? So at the boundary of continuous and discontinuous conduction, right? So at boundary of continuous conduction mode means CCM and discontinuous conduction mode means DCM. So at the boundary, okay, what is the boundary? For continuous conduction mode, okay, for continuous conduction mode, your minimum current will always be positive. For discontinuous conduction mode, your minimum current will be negative. But at the boundary, what you will be having is I minimum equal to 0, right? Now I minimum is calculated by IL average minus delta IL by 2. So you will equate it to 0, or IL average should be equal to delta IL by 2. What kind of converter we have? We have buck converter, right? This is buck converter. In case of buck converter, the IL average value is I naught upon 1, sorry, it is I naught only, right? Delta IL is D 1 minus D Vs over FL, right? Further, you can write I naught to be dVs over R, and here it will be D1 minus D Vs over 2 FL. Now dVs will be cancelled, and what we will get is that 1 minus D, this is equals to 2FL over R, or you may also write it 2L upon R into T, right? So what will be the value of D? The D value will be 1 minus 2L upon R T, and this you can utilize as formula if you can practice that. Otherwise, no need to do that. You will apply condition and you will get it, okay? So what is the value of D? D is 1 minus 2L over RT, or 1 minus 2 FL over R. Do we have everything? 1 minus 2, what is the frequency? 50 kilohertz, right? And what is the inductor value? 15 millihenry. So 1 minus 2 into 50 kilohertz into 15 millihenry divided by the resistance, which is 2 kilo ohm, okay? So when you will solve it, what you are going to get? 0.25, yes, 0.25 will be the duty ratio, which I can see is that Meghanathan is getting, Bindusri is getting. Very good, very good. Your preparation is Very good. If you can solve, if you can get answer of these kind of questions, that means you are on right track. Correct? So for buck converter, this might be a formula that you can utilize directly to calculate duty ratio, right? Or otherwise, if it is required, you can calculate this in this way. This is for buck converter. They may ask it for boost converter. They may ask it for buck boost converter as well. Process will remain same. Okay. So in this way, you have seen one more formulas, 1 minus 2L by RT for buck converter. For boost and buck boost, it will be different, right? So what I can see that you people are able to give the answer of this question, and the answer is correct. That means this question is clear, right? Now see another question. The IGBT shown in figure is operating at a switching frequency of 40 kilohertz. So we have been given the switching frequency, which is 40 kilohertz with a duty ratio of 0.5 or 50%. The ratio of average switch current, the ratio of average switch current to the average diode current will be what? Okay, average switch current to average diode current ratio will be what? Okay, and what kind of converter we have? We have boost converter, right? This is the boost converter. So let me check who can answer this question, and I am giving you 3 minutes for that. Okay, let me have a look that who can answer this question. You people can solve this question. Wow, that's great. Bindu, Medha, you are getting answer as 1. And Chetan, you are asking for VS. It's 200 volt, right? Harini is also getting 1. Very good. What about others? Yes, Dev, Niharika, Meghanathan, Chetan, what is your answer? And Gautam, Dharmendra, are you people getting 1? So last 40 seconds. Niharika is also getting 1. Very good. Anybody who is getting a different answer? Okay. Yes, that's right. 1 is the correct answer. Okay. We have to calculate the switch current and diode current average value. Okay. Have a look. Where is the switch? This is the switch. Okay. Now you tell me that switch. Okay. Krishna is also getting 1. Very good. So switch current. Switch will carry current when it is on. When it is on, Okay, it is carrying current when it is on, right? On means D, and when it is on time is being symbolized by the term D, and when it is carrying current, it is carrying the same inductor current, isn't it? It is carrying the same inductor current. So we can calculate the switch current in terms of inductor current, right? And D is the term used to symbolize the on period. Okay, switch will be carrying the current during the on period. Now, when switch is on, diode is off. When diode is on, switch is off. So when the diode will be on, right, at that time your switch will be off. So when the diode will be on, it will be carrying what current? It will also carry the inductor current in off period. Off period is being symbolized by the word 1 minus D, and it is carrying the same inductor current, right? Now this you can cancel. So what you are getting as ratio is D over 1 minus D, and D is given 0.5 upon 1 minus 0.5, which will give you a result 1. Okay, so most of you have solved this question correctly. Very good. Okay, you people are in a very good touch of preparation, right? I hope that those who are not able to solve, it is clear to them as well. Got it? So now we can move to the next question, and this is our next question. A boost converter, as shown in the figure, is feeding a variable resistive load, as shown in the figure, is operated at a switching frequency of 83.5 kilohertz. So I can write it here. Switching frequency is 83.5 kilohertz. It gives an output voltage of 78 volt from 48 volt supply. Input voltage is 48 volt. The value of R in ohm that will make the inductor current just discontinuous. Okay, we need to calculate the value of inductor current that will make we have to calculate the value of R that will make the inductor current just discontinuous. Means we are talking about the boundary, right? We are talking about the boundary. So at boundary of CCM and DCM, what do we get? I minimum is equal to 0, right? Or IL average is equals to delta IL by 2. IL average here is I naught upon 1 minus D. Delta IL here is dVs over FL. Okay, if suppose you do not know the formula. Okay, so from here what you can do, I naught can be written as, I naught you can further write as Vs over 1 minus D square into R. This is equals to dVs over 2FL. L is LC. If you do not know the formula, okay, then you can write it like this. Now from here what will be LC? It will be D 1 minus D square R over 2F. Now do we have all the data? Yes, we have. Inductor value is given 100 microhenry. D value is how much? We don't know. So D value we will be calculating from this given data. Okay, so if I am going to calculate the D value, just see, V naught is Vs over 1 minus D because it is boost converter. So 1 minus D will be Vs over V naught. How much is Vs? 48. How much is V naught? 78, right? So how much is D value? From here when you will solve it, 1 minus D is coming 0.62, right, and D will be coming 0.38. So in this way you can calculate the D value, right? Now just put here. So D is 0.38, 1 minus D is 0.62, square R we have to calculate, divided by 2 into the frequency is how much? 83.5 kilohertz. Okay. Now when you will solve this equation, you will get the value of R, and that is coming 114. When you will solve this equation, you will get R value as 114.32 ohm. Correct? How many of you have obtained this answer? Tell me. You can use this formula directly if you are able to remember. If you are not, then you can derive. Okay? So, just see, we have done the derivation and then we have used the formula. How many of you are getting the same answer? 114.32 ohm is the value of resistance that I am getting. Very good. Chetan is getting same answer. Very good. Okay. I hope that all of you are getting the same answer. Right? So, is that question is clear to everyone? Can we move to the next question if you are getting the answer? Correct? So, let me move to the next question, and this one is the next question. In the figure shown below, the switch is operated. Just see the figure. What is the presence of inductor? Inductor is present at the middle. So, if it is present at the middle, it is buck boost converter, right? It is a buck boost converter. Got it? Now, just read the question. In the figure shown below, the switch is operated at a frequency of 25 kilohertz. What is given? The frequency. How much? 25 kilohertz. The duty ratio is 0.25. Power absorbed by the load means output power is 2450 watts. Then the average value of inductor current will be what? Okay, and your time starts now. I think that you can solve this question, and not more than 2 minutes you will take. Okay, so solve it, guys, and tell me what is average inductor current. If this much data is given, what is going to be the average inductor current, right? Output power is given, duty ratio is given, frequency is given. You have the circuit diagram in which source value, inductor value is also given. Calculate that what is going to be the average inductor current. .45. Yes, that's correct answer. Chetan and Meghanathan, you have answered it correctly. Okay, Harini, your answer is not correct. Bindu has also answered it correctly. Very good. So, see, we have been given the output power. How you will calculate the output power? Output power will be V naught into I naught, simply because it's a DC circuit, right? Now, output power is given 2450. Okay, V naught we don't know, but V naught in buck boost converter is D over 1 minus D times Vs into I naught, right? Now, 2450, and here we have D over 1 minus D. D is also given, we can write it. D is 0.25 upon 1 minus 0.25. And how much is Vs? Vs is 100 into I naught. So only I naught is the unknown. So once you will calculate it, you will get I naught, and that I am having the value of I naught is 29.94 ampere, right? Then we have to calculate IL average. So whether it is boost converter or it is buck boost converter, IL average is I naught over 1 minus D. What is I naught? It is 29.94, and what is D is given 1.25. Once you will solve it, you will get 54.44 amperes, right? So Harini, where you have mistaken? And very good, Bindu, Meghanathan, Chetan, you are getting correct answer, right? Just keep this momentum, your preparation is very good, right? So you can cross check, guys, that where you have done the mistake and why you are not able to solve it. Suppose you are not getting the answer and you are not getting an approach how to deal with this problem. Got it? So after that, let me move to the next question. Now this is a very good question because this is having discontinuous conduction. Okay, if you will just see the PYQs, they have given 99.99% a problem from continuous conduction. Once they have given in 2018 or I think in 17 a problem from discontinuous conduction. So we have discussed that particular thing as well. Okay, now in a buck boost converter, the current waveform through the inductor is shown in the figure. So if you look into this waveform, it is discontinuous, right? Then the output voltage is how many percent of input voltage. So the ratio of output voltage is how much percentage of input voltage. Okay, this is what we have to calculate here. Okay, so first of all, let me see that how many of you are comfortable in discontinuous conduction. It's not a different topic, right? Your time starts now. Let me see that who can solve this question. Okay, and in the meanwhile, I'll just prepare for it. .85. Okay, 42.85. You can cross check once again, okay, because I am getting 60%. Just cross check. I am getting 60%. So see, this is a buck boost converter, right? This is a buck boost converter, correct? This is a buck boost converter. Chetan is getting 60%, and that's correct answer, right? Now, see, in this buck boost converter, we have been given the waveform of inductor current, right? So let me draw this waveform of inductor current. Inductor current first increases in 0.3 t, then it is decreases in 0.8 t, and then it becomes discontinuous, right? See, so this is 0.3 t, this is 0.3 t, this is 0.8 t, and this is t. So how much is this duration? This duration will be 0.5 t. Okay. How much is this duration? This duration is 0.3 t, right? Now, when inductor current is rising, it is the on period. So can you tell me that when the switch will be on, at that time what is going to be the inductor voltage? This is inductor current. Now let us plot the inductor voltage. So when the switch will be on, at that time what is the inductor voltage? It is equals to Vs, okay? So it is equals to Vs. Now when the switch is off, then this part of the circuit will be active, and then what will be the inductor voltage? Minus VL plus V naught equals to 0. So VL equals to minus V naught, right? You will get VL equals to minus V naught, okay? And after that there is no inductor voltage, then again it will follow the same thing. So here it is Vs, here it is minus V naught. Tell me, is that understood first of all? Okay. Because we need to calculate the output voltage, for that we need the inductor current waveform, right? So that is why we have done that. Now what you will do, so this time is 0.3 t and this time is 0.5 t, okay? Now what we are habituated of doing, that average inductor voltage will be 0. That means the area under this waveform will be equated to 0, right? What is this area? Height into width, means Vs into 0.3 t. Now what is this area? Height into width minus V naught, and what is the width? 0.5 t, okay, and equate it to 0. Then when you are solving, you are getting how much? From here you will get Vs into 0.3 t, this is equals to V naught into 0.5 t. T and T will be cancelled, and you will be getting V naught equals to 3 Vs over 5 or 0.6 Vs, or you can write that output is 60% of input, right? So answer is 60%. Megha Nathan and Medha, why you are getting 42.85, 42.86? How you have done that you are getting 42 point something? Tell me. What exactly happened, where you have mistaken, okay? And are you assumed continuous conduction mode criteria? And then in continuous conduction mode, if you have assumed, then what you have done? Okay, then you might have taken this time as more time, right? Okay, you have taken D directly, okay. So if it is a discontinuous mode problem, now you got a clarity what you have to do, okay. So for discontinuous conduction mode problem, draw the waveform like this. Whenever we are talking about average voltage, we need the inductor voltage waveform, and then we have to calculate the area for the available waveform, okay. If you will do it like this, you will get it done in this way, okay. So correct answer is 60%, right. D you have taken as 0.3. No, we don't have to do that, okay. So I hope that this question has given you a learning, okay. Now after this question, we have another question, this one. See this one. A DC to DC converter is used in regeneration braking mode, okay. Regenerative braking. What is regenerative braking? The DC motor will be supplying to the source, okay. Regenerative braking means the DC motor will be supplying the power to the source. So power flow will be from load towards the source side, got it. This is the meaning of regenerative braking mode. It is operated on a duty cycle of 50%. The average value of armature current is given 91 ampere. So output current, armature current will be the output current, and that is given 91 ampere. It is continuous and ripple free. The correct statement about the power is that power is this much and delivered by the source, received by the source, delivered by the source, received by the source. Okay. So we have to solve this question. Let me give you some time. Okay, think about it and let me see whether you can approach towards the right answer. Think about it. Regenerative mode, I told you. In normally power flows from source to the load. In regenerative mode, so if it is operating in a normal mode, it will be taking power from the source. If it is operating in the regenerative mode, means it is operating as a generator, so it will be feeding the power to the DC source, right? Now calculate and tell me what you will be getting. This Vs is given 580 volt. Okay. Okay, so see, I am telling you that regenerative braking mode, so the motor is acting as a generator and it is feeding to this supply. Okay. Now, so when the switch is on, the inductor polarity will be this polarity, right, and inductor current will be flowing in this way. So when the switch is on, okay, and just see the output voltage will be here, that you will be getting. This is the output voltage, correct? This is the output voltage that you will be getting, right? So now have a look. When the switch will be on, what will be the output voltage? It will be 0, correct? When the switch is on, the output voltage will be 0, right? Now when the switch will be off, at that time the inductor polarity will be like this, and due to this polarity diode will get on, and now the current can come here in this part of the circuit. Okay, at that time you will be getting some output voltage, because switch is off, so output voltage you may get. So what is the output voltage? You may get some output voltage. V0 will be having some value, right? So this will be the waveform. And what value V0 will be having? Just see, V0 will be equals to this Vs, because diode gets on, right? So V0 will be having a value Vs, correct? V0 will be having a value Vs. So in this way we have plotted V0, right? Now looking into this V0, so you can say that V0 is available in 1 minus dt or off type, right? This is when the switch is on, this is when the switch is off, right? So V0 you are getting right now during the off period. Off period is being symbolized by 1 minus d. So 1 minus d times Vs, right? How much is the duty cycle they have given? 0.5. How much is Vs? 580, right? So how much you will get? 290. Output voltage will be 290. Now we have to calculate the power. So power will be V naught into I naught, right? V naught is 290 and I naught, average armature current will be basically the I naught current, okay, which is given 91. So when you will write here 90, so 290 into 91, 290 into 91 is how much? It is 26.39. 26.39. So this is wrong, this is wrong. 26.39 received by the source, okay, both the options are same, है ना? 26.39 received by the source, any one might be correct. If I change it to delivered, right, then option B will be correct. So B or C might be correct, right? 26.39 received by the source. What I can do, I can change this to load. So now B is correct, right? Now B is correct. And as I told you that in regenerative braking, the motor will be acting as a generator. It is supplying to the source. So obviously the load will be delivering and the source will be receiving. Okay, so B will be the right answer. And what I can see that Harini, Meghanathan and Bindu, you have given correct answer. Wow, proud of you. Really very good. Okay, if you are able to solve question like this, you can do anything. Okay, so I hope it is clear to others as well. Okay, I don't know whether you have solved this kind of question in your preparation or not, but you have now got a flavor of this variety as well, right? So next time, if suppose such a case will be there, you will be able to apply your concepts. Got it? Now after that, now this question, just see this one, parallel converters. Okay, so which of the following statements is or are correct for the circuit shown in the figure? If you see into this circuit, the inductor is present on the load side, so it is buck converter, and what we can see that they have connected two buck converters in parallel. Okay, and two buck converters are connected in parallel, so this IS will be dividing here itself into IS1 and IS2, right? Now which of the followings are correct? The switches are operated 180 degree out of phase, yet that is a correct statement. Okay, because if converters are connected in parallel, the inductor current has to be phase shifted, and this is the phase shifting amount, where N is the number of converters, right? You have to do the phase shifting. Inductor current cannot increase at the same time, right? So A is correct. Second is the switches are operated in phase with each other. No, this can't be done, right? Inductor currents are 180 degree out of phase with respect to each other. Yes, if the switches are operated at 180 degree out of phase, then obviously the inductor current will also be 180 degree out of phase with respect to each other. Each inductor supplies one of the load current and output power. Okay, so IS is dividing itself into IS1 and IS2, right? If these converters are identical, then IS1 and IS2 may be equal to each other, so they may supply half the power and they may share half the source current. So this can also be a true statement, right? So related to parallel converter, this is a very good question. Now calculative part, so what you can see that inductor current 1 and 2 will become inductor current, total inductor current, or IL1 plus IL2, right? So average inductor current, it will be equals to I naught. Okay, and as you can see that source current, you know, it is D times I naught, right? And if suppose we will be asked to calculate IS1, IS2, then it will become IS by 2 or D I naught by 2. So numerically be prepared to calculate things like this and like this, and three statements are covered. So in one question, through this one question, we have covered that how the parallel converter will operate, right? It is known as interleaved converter or parallel operation of converter. Okay, only one converter will be active at the time, means one switch will be on, other will be off. So the inductor current will be phase shifted. What is the phase shifting amount? 360 by n, where n is the number of converters. Since we have two converters, so amount will be 180, right? So theoretical part of this, numerical part of this, be ready for this kind of question as well. Question from parallel converter was asked last time in 2018. Since then they have not asked a question from this topic, so be ready this time, okay? Anything out of this may come, right? So I hope that it is clear, right? I hope that it is clear. The PDF of this session will be immediately posted into the Telegram group. So if you have not joined our Telegram group, you can join the Telegram group. The link is given in the description box, okay? Now, so enough of this DC to DC converter. Now we are moving into the rectifiers, okay? So rectifiers, the weightage 2 to 3 marks, important topic, single phase, 3-phase rectifier and effect of source inductance. These are the important topics from this chapter, okay? Let us start the questions. So this is the first question that I am having. What is given here? The source voltage and current of a single phase AC to DC converter, means rectifier, is voltage is having only one frequency, while the current is having fundamental frequency, third frequency and fifth frequency component. What is the total harmonic distortion? So definitely if the current is having multiple frequency term, total harmonic distortion will occur on the AC side of the converter, and we can calculate that, okay? So what will be THD? So THD, total harmonic distortion, is under root 1 by CDF square minus 1. How to calculate CDF? CDF is fundamental RMS current divided by the total RMS current, right? Fundamental RMS current, this is the fundamental current, so its RMS value will be maximum value divided by root 2, and total RMS current will be the sum of individual RMS square. 10 root 2 by root 2 will be the fundamental RMS current, square of it, then 5 root 2 by root 2, third harmonic component, square of it, then root 2 by root 2 and square of it. When you will be solving it, you will be getting 0.89, okay, as the value of CDF. Now come back here and put the value 1 upon 0.89 square minus 1, okay, then you might be getting 0.1235, but answer we have to give in percentage, so it will be 12.35% of total harmonic distortion, right? So if the current waveform, voltage is sinusoidal, current also has to be sinusoidal and only having fundamental component, but it is having first, third and fifth harmonic component because of the circuit operation. So those will travel onto the secondary side and they will distort the waveform, and they have caused 12.35% of total harmonic distortion, right? Whether these answers are correct, just confirm me. Chetan, 0.51 is what? CDF or THD? This will be 10 by under root 126, okay? So 10 by under root 126. Under root 126 will give you something around 11 point something. So when you will divide 10 by 11 point something, you will get 0.89, okay? 0.51 is not possible. Then when you will put the values here, I think you will be getting this answer, okay? Anybody is getting the same answer? (51.23). 51.23 is what? THD. This one. THD is 0.51. Okay, so maybe my answer is wrong. Okay, what you are getting? 0.5123 or 51.23%. Correct? Maybe. So I have done calculation from my side, maybe this one is wrong. Okay, I accept your answer. 51.23 is the right answer. Very good, Krishna. Very good, Bindu. Very good. Okay, so I think you people are able to solve this question. Now see this one. A three-phase converter charging a battery, three-phase full converter is charging a battery from a three-phase supply of 230 volt 50 hertz. The battery EMF is 198 volt and internal resistance is 0.6. So E is 198 volt and the internal resistance is 0.6 ohm. On account of inductance connected with the battery, charging current is kept constant at I naught. Charging current means output current is kept constant at 20 ampere. If the power is flowing from DC source to the load, right? Power is flowing from DC source to the load, right? If it is flowing from DC source to the load, right, power is flowing from DC source to the AC, right? If the power is flowing from DC, power is flowing from DC load to the source, this is what they are trying to say, DC load to the AC source, right? Then the firing angle delay will be, then what is going to be the alpha value is what you have to calculate. Right, in rectifier we know that load is DC, source is AC, right? So if the power is flowing from DC to AC, means the power flow is reverse. Normally the power should flow from AC to the DC in rectifier, but it is flowing from DC to AC. That means the alpha value is less than 90 or greater than 90. We are sure that alpha should be greater than 90. So we can eliminate this option, we can eliminate this option, either of them, C or D might be correct, right? So what is going to be the load KVL? KVL will be, when we have RLE type of load, KVL is normally V naught equals to E plus I naught R. When alpha is less than 90, the KVL becomes minus E plus I naught R when alpha is greater than 90, correct? Now it is a three-phase full converter, so output voltage will be 3 VML over pi cos alpha minus E plus I naught R, right? Now just put all the values, 3 VML. This is given the source voltage, okay? And it is not mentioned that it is phase. So normally given voltage is the line voltage. We have to calculate the maximum value of it. So root 2 times 230, okay, divided by pi, this is 3.14, minus E minus 198 plus I naught into R, okay. When you will solve, we forget to write cos here. So when you will solve it for alpha, are you getting 126.77 degrees, right? So this is going to be the answer, okay. So D will be the right answer. Correct, okay. You should know this thing, even in single phase full wave converter or in three phase converter, you should know that what will be the KVL when alpha value is what, okay. When alpha value is less than 90, power will flow from AC to the DC, okay. We will apply KVL in this way. When the power is flowing from DC to AC, that means because of alpha is greater than 90, this might have happened, okay. So you need to know that how to apply KVL in such a condition. So are you getting this answer? Tell me, are you getting the same answer? Alpha is 126.77, okay. So by just referring to the question's language, we just got an understanding that alpha definitely might be greater than 90 because power flow is from DC to AC side, okay. So is that clear? Are you getting same answer? Medha, Niharika, Bindu, Bhavani. Are you getting same answer? I hope you are getting, right? It's a easy question, okay? Now, after that, just see this one, okay? A single phase full converter delivers power to a resistive load. Single phase full converter, all thyristors are there. It is delivering power to a resistive load, right? It is delivering power to a resistive load, right? Source voltage is 230 volt. The RMS output current will be, what is going to be the RMS output current, right? You have to calculate what is going to be the output RMS current, right? So it is a full wave converter. So whether you will apply 2 Vm by pi cos alpha average voltage, and what is the RMS voltage of full converter? RMS voltage of full converter is Vs only, right? So whether you are going to apply the same formula? No, because that formula we have derived for RL load, right? For RL load, output voltage average output voltage will be 2 Vm by pi cos alpha. RMS voltage will be Vs or Vm by 2. But here we have only R load. So for that the formula will change. How? Let me just tell you. Okay, so be very careful about the loads given in rectifier. So if this is our source voltage waveform, and if suppose this is going to be the output voltage waveform, then see the source voltage, right? Let's suppose that this is alpha, this is pi plus alpha, and this is 2 pi, this is 2 pi plus alpha. So during during the positive cycle, T1, T2 will be on, okay? So T1, T2 when it will be triggered, they will be following the input waveform till pi, right? After that, because the load is resistive, so when the negative cycle will start, T1, T2 will be off and there will be no voltage unless other pair will be triggered. So other pair you are triggering at pi plus alpha, correct? Just see. So from pi plus alpha to 2 pi you will be getting this waveform. Then negative cycle will be over, positive cycle will be starting. So T3, T4 will also be get off, okay? Then at 2 pi plus alpha we will be getting the same sequence. So here T1, T2 operated, and here T3, T4 operated, and in this duration none of the switches will be on because the load is resistive, okay? If the load might have been inductive, output were forced to follow the input from pi to pi plus alpha, that we know, okay? But here the load is resistive, correct? So now if you will calculate the RMS voltage of output, okay, this is the output voltage waveform. If you will calculate its RMS value, then what you are going to get? So just see, from here till here, this portion of the waveform is repeating itself. So the time period is 1 upon pi, and out of that you are getting output voltage from alpha to pi, and at that time your output voltage is equals to the input voltage, which is Vm sin omega t. You will square it and d omega, right? Now how to solve such a case? So you know the trick that if you have to calculate RMS value, it is Vm upon 2 into the time period, higher limit minus lower limit, plus half sine 2 omega t, lower limit higher limit, power 1 by 2. So if you will apply the same trick here, then see Vm by under root 2 into time period is pi, higher limit is pi, lower limit is alpha, plus half sine 2 omega t, and you will write lower limit as alpha and upper limit as pi, whole to the power 1 by 2, okay? So see, if you will do this exercise, you are getting these things, correct? I hope that it is clear. Now after that just solve it. So what you are going to get? Vm by under root 2 will be Vs upon under root pi, pi minus alpha, and from here you will get 1 upon 2 sine 2 alpha, right? Now how much is Vs? Just put all the values and see what you are going to get. How much is Vs? So Vs is given 230 volt upon under root pi. Pi minus your alpha value is 60, so pi by 6, okay, plus half sine 2 into pi by 6 power 1 by 2, right? Pi minus pi by 6 will be 2 pi by 3. Write this value in radian. Do not forget doing that, okay? Write this value in radians. So pi value will be putting 3.14. This is angle, right? So now once you will calculate, you will be getting your output RMS voltage as 206.035, right? This is going to be the RMS output voltage. Then what is going to be the RMS current? So output RMS current will be simply output RMS voltage divided by the resistance. So voltage you are getting 206.035, resistance value is given 10, so you will get 20.60 ampere as the current, correct? This is how you will be solving it. What is the difference between this problem and any other problem? Here the load is given resistive, so we cannot be, and the converter is full wave converter, so we cannot use the formula 2 Vm by pi cos alpha. That is for RL load or RLE load, got it? That is for RL or RLE load. Here the load is resistive. For that we do not have any idealistic formula for average value or RMS value. If suppose it is RL or RLE load, RMS value of the voltage will be Vs or Vm by 2. In full converter we know that it is going to come like that, okay? But we cannot use those directly. For resistive load we need to calculate it in this way, right? Then you can calculate the current. So I hope that it is clear. So this question I have taken just to make you remind of this fact that all those formulas that you have derived in class is for RL load. Majority of the loads are RL load, okay, not for R. For R you need to do this exercise again, correct? I hope it is clear to everyone, okay? So always take a reminder when the load is R. Here they have asked about the average value, sorry, RMS value. If they might have asked for average value, many students will do the mistake. They will use 2 Vm by pi cos alpha as the average voltage, simply divide by R and get the answer. That is wrong answer, right? Nothing, no problem. For average value there will be no under root and no square, and just integrate it, you will get it, okay? Simple integration you have to do. If you are calculating the average value, there will be no under root and there will be no square. Simple Vm sin omega t is what you have to integrate, you can get it, okay? So I hope that this is an alarming question, okay? This is an alarming question, that when you have to use what formula, when you have to calculate, correct? Now after this question, this is the next question. See this one. A 3-phase full bridge converter is connected to supply voltage of 220 volt line. This is the source voltage at a frequency of 50 Hz. The source inductance Ls is 3.2 millihenry and the load current at the DC side is 15 ampere constant current. The average power absorbed by the load in kilowatt at a firing angle alpha is 45. What is the average power absorbed by the load is what we have to calculate, right? Average power we have to calculate. Average power will be V0 into I0. I0 is given. If we will calculate V0, we will be done with the power. Now we have to calculate V0, and what you can do, that what you can see, that source inductance is there. So because of the source inductance, there will be net reduction in the voltage, okay? So what is the new average voltage? So V0 average new, that will be V0 average old minus the reduction factor, right? Now V naught average volt, because it is a 3-phase full bridge converter, so it will be 3 VML over pi cos alpha, and the reduction factor will be 6 F LS I naught, right? If this would have been a full wave converter, here we will be writing 2 VML upon pi cos alpha, here we will be writing 4 F LS I naught, right? If it is a half wave converter, we will be writing Vm by pi 1 plus cos alpha here, and here we will be writing F LS I naught. Okay, so you should know the old average value formula for all the converter. You should know the reduction factor. For 3 phase 6 FLS I naught, for single phase full wave 4 FLS I naught, for half wave FLS I naught, simply like that. If you know that, you can solve this question. Now VML is the maximum value of the line voltage. So the given value is line voltage, right? So line voltage RMS value is given. For maximum value you need to multiply with root 2 and 220 divided by 3.14. Cos of alpha value is 45, right? Minus 6 F. What is F value? F value will be 50, right? So minus 6 into F 50, LS 3.2 millihenry, okay, into I naught is 15, correct? So when you will solve it, the final answer that I am having for it is 195.79. Okay, or let me write it individually, then you will see the difference. It is 210.19 and this reduction amount is 14.40, and then finally you will be getting 195.79. Okay, so you can see this amount. The old amount is 210.19, reduction amount is 14, and the new voltage is reduced voltage. This is the effect of source inductance. The net voltage will be reduced, right? This is the output voltage. Then you can calculate the current. 195.19 into 15. Okay, so what you will be getting is 2.94 kilowatt, right? 2.94 kilowatt. Very good, Chetan, you are getting the correct answer, right? So in this way we have to solve this question. The same question may be repeated for single phase, may be repeated for single phase half wave converter, and this is the way you have to do it. Instead of control converter, they may ask for uncontrolled converter. In that way alpha might be 0, right? So all those techniques and things you know that you might have covered in your classes, right? So I hope that this is clear and you are getting the answer. Got it? The next question, this one, just see this one. A 3-phase 3-pulse converter is connected to load requiring a ripple free current. A freewheeling diode is connected across the load. Thyristor having firing angle alpha 60, then the RMS value of diode current will be. RMS value of this diode or freewheeling diode will be what? Okay, this is what we have to calculate. Sir, the supply voltage given is always RMS. Yes, in AC, so in the case of AC, the given voltage is always RMS, right? In case of 3-phase, the given voltage is always line voltage unless otherwise specified. Okay, if the line voltage is a phase voltage, okay, so if phase voltage is given, correct, then how you will get VML? Just see, first of all you will convert this phase voltage into the line voltage. How you will get the line voltage from phase voltage? Tell me. If phase voltage is given, how you will get the line voltage? You will multiply root 3, okay, into the phase voltage, correct? Then you will get the line voltage. Now in order to get the maximum value of this line voltage, again you will multiply with root 2. So it will total become root 6 of V phase, correct? So if the phase voltage is given, then you will multiply with root 6. If the line voltage is given, only you will multiply with root 2, and the given voltage is always RMS value. Correct? I hope it is clear. They may only change these things, nothing else they can do. Now focus on this question. So what will be the diode current value? For before that, the question is for what duration the diode will conduct. Okay. So let me tell you, just see. If suppose you are not using diode, okay, so any switch will conduct for what duration? If suppose I take an example of T1, okay, so if I am talking about T1, so T1 will conduct for omega t equals to 30 plus alpha to 120 plus alpha, right? 30 plus alpha to 180 plus alpha. Sorry, we have to add 120, 30 plus 120 will be 150, right? 150 plus alpha. So what you can see that the difference of duration is 120 degree, right? Any switch will conduct for 120 degree. What is alpha in our case? Alpha in our case is 60. So the switch will conduct for 90 to 210, correct? Switch will conduct for 90 to 210, right? Now let me tell you something. If this is my AC source, correct, where what is this? This angle is 120 degree, this angle is 360 degree, okay, and we need to get 90 and 210, so 90 might be here, 210, so here it will be 270, so 210 you will get somewhere here, correct, 210 you will get somewhere here. Got it? Now you will trigger your switch at this point of time, okay. So when you will trigger your switch, switch will immediately reach to the highest peak point voltage, okay. Then it will follow the input voltage up till 180. It will follow the input voltage up till 180. Now what is the load voltage? Load RL load. So because of inductive load, it will keep on following. It will keep on following this inductive, this load voltage up till the angle 210, correct. So you should have get output voltage from 90 to 210 if there is no freewheeling diode, correct. Now what will happen? Because of the freewheeling diode, okay, because of this freewheeling diode, what will happen? The moment you will reach to 180, the negative cycle will start. So when the negative cycle will start, inductor current should have become 0 and inductor will reverse its polarity, right. So when the inductor will reverse its polarity, then what will happen? Freewheeling diode will be conducting. So your freewheeling diode will conduct here, correct. Your freewheeling diode will conduct from here to here. Then after that your other switch will start, correct. So if I have to tell you that for what duration the freewheeling diode is conducting, so freewheeling diode is conducting for this duration, and what is the available duration? The available duration is 90 to 210, right. Available duration is 90 to 210, okay, out of which your freewheeling diode is acting only for 30 degree, right. So if I have to write that what is going to be the diode current RMS value, then it will be in terms of I naught, and diode conducts for 30 degree out of available 120 degree, okay. Total duration available is 120, out of this it is acting only for 30 degree, or I can write it I naught, just see 30, how I will be getting is, I can also write is alpha minus 30 upon 2 pi by 3, right. Alpha is 60 in the given case, 60 minus 30 will be 30, 120 is 2 pi by 3. So this is an ideal formula that you can use for practice, okay. Just see how we have derived the formula right now as well, okay. So if we will put the values, I naught is given how much? 10 ampere and 30 over 120, so 10 upon 2, or we will get 5 ampere, Correct? How many of you are getting 5 ampere as the answer? Tell me guys, how many of you are getting 5 ampere? No one? This is how you could have approached for this question, right? If there is no freewheeling diode, okay, then inductor voltage and current might have followed this path, okay, it might have followed this path, correct? Now what will happen? Thyristor will conduct, or T1 will conduct only for this duration, because freewheeling diode is there. So when the negative cycle is reaching, naturally freewheeling diode will be conducting, so it will conduct in this duration, and that duration is 180 to 210, that means 30 degree. Got it? So this might be the formula, or you may use this trick to solve it. Is that clear to everyone? How many of you are clear with this question? Tell me. Is that part is clear? Give me a response guys. In the chat box you can reply. It's a very, very good question, you know. Right? I hope it is clear. Now moving towards the next question. See this one. A single phase half controlled. So it is a full bridge but half controlled because diodes are used along with the thyristors, is connected to an RL load as shown in the figure. If the load carries a constant DC current of I naught is given 35 ampere, the average current through T1 will be, what will be the average current through the T1 is what you have to obtain. Firing angle is given 45, okay. So what will be the average current across T1 is what we need to get, okay. So let's see. For that we need to plot the waveforms, then we will get an idea. So if suppose this is the source voltage waveform, after that if suppose this is the output voltage waveform, right, then if suppose that this is the load current waveform, and then finally if we draw the current waveform for switch T1, okay, then what we will be getting. So this will be what? First cycle, this will be the second cycle, okay. So let me first of all plot the input AC voltage. This is my input AC voltage, right, source voltage. Now let me plot, this is for alpha, okay, this is pi plus alpha, and this is 2 pi plus alpha, okay. So quickly you can plot the waveform: alpha, pi, pi plus alpha, 2 pi plus alpha. Got it? Now let us plot the output voltage, okay. So see, load is RL type, right. What kind of load we have? Load is resistive and inductive load, RL load we have, okay. Now when there is positive cycle, you will trigger T1 and D2, okay. So T1 and D2, they will carry the voltage, okay, and they will keep on following the input voltage, right. So from alpha to pi there is no problem, they will follow. When pi will be reached, negative cycle is starting. Because of negative cycle what will happen? Because of negative cycle what will happen? D1 will be on, D2 is already conducting, D1 will be on, so D1 and D2 will conduct here, and when D1 D2 will conduct, it's a direct short across the load, output voltage will be 0. So who conducted here? D1 and D2. Who conducted here? It is T1 and D2, correct. Now inductor will store energy here, inductor will release energy here. Now when negative cycle is started, okay, then T2 and D1 can be on, D1 is already on, we have to trigger T2, so T2 and D1 will be on, and now they will carry the output voltage, they will follow the output voltage. When 2 pi will reach, okay, so who conducted here? T2 and D1. When 2 pi will be reached, okay, then positive cycle starts. So because of the positive cycle starting, T2 and D1 were conducting, D1 is already conducting, during positive cycle D2 will be on, right. So again what will happen? D1 and D2 will conduct, okay. So here what you can see, D1 and D2 is conducting, so output voltage will be 0, right. Then we can write that here also D1, D2 were conducting. So I can say that output current is constant throughout because it is being carried by either pair of the switches, right. I hope it is clear. Now we have to calculate T1. So if I plot IT1, okay, so just see the duration where T1 is conducting. Whether T1 is conducting here? No. T1 is conducting only from alpha to pi, and then it will all another time it will get on at 2 pi plus alpha. So alpha plus pi 2 pi, and then 2 pi plus alpha, it is another time it is getting on, and its amplitude is I naught here, okay. So first of all, tell me whether these waveforms are clear to everyone, okay, whether these waveforms are clear. When we are having positive cycle, then T1 and D2 will be forward bias, okay. When we will be having negative cycle, okay, when we will be having negative cycle, T1 will be reverse bias, okay, and D2 should be reverse bias, and D1 will be forward bias, correct. But inductor will be having this polarity initially, then it will reverse its polarity and it will maintain D2 into conduction. So what will happen, D1 and D2 will be on and V0 will be 0, correct. Then during the negative cycle, T2 and D1 will be on, okay, and then when they will be off in positive cycle, again D1, D2 will conduct. So every time from pi to pi plus alpha or 2 pi to 2 pi plus alpha, D1, D2 will be conducting and making the voltage 0. So I hope that these waveforms are clear to you, and out of those waveforms I have plotted T1 waveform, okay. So when you can see when T1 is conducting, and you can have that waveform. Now what we have to calculate is the average current through T1, okay. So IT1 average, just see the periodicity. So from here to here it is one shape of the waveform. So what is the time period? 2 pi. Out of that time period 2 pi, it is available for alpha to pi, and at that time its value is its value is I naught, okay. So what we are going to get? I naught pi minus alpha upon 2 pi, that will be the formula. Then when you will put the values in the formula, I naught is how much? 35, okay, and pi minus alpha is given 45, pi minus pi by 4 upon 2 pi. So when you will solve it, you will get 21.4, correct. This will be the answer, got it. So just see, in rectifier you may get a straightforward question, and in rectifier you may get a question in which you have to apply some reasoning, and there your conceptual knowledge will help you, okay. So I hope that when you have covered rectifier, whoever faculty has taught you rectifier, they might have covered this conceptual knowledge, and with this conceptual knowledge you can analyze the rectifier questions, got it. So I hope that this question will be done by you if you will be giving the GATE exam, right. So is it clear? Can we move to the next question? Okay. Now, so this much I have from rectifier. Now inverters, okay. Inverters can give you 2 to 3 marks. Important topics are VSI and CSI, single phase and 3 phase inverters, very important, okay. Then what is very important is pulse width modulation techniques, or we can say voltage control of inverter. One such formula is there, okay. If you know the Fourier series, if your Fourier series knowledge is very good, inverter is nothing for you, right. Let's see the question. So this is the first question that I have. A 3-phase bridge inverter delivers power to a resistive load from 440 volt DC source for a star connected load of 12 ohm per phase. The ratio of power delivered to load when inverter is operated in 180 or 120 degree mode, okay. If it is operating in 180 mode, power will be 3 times V phase square upon R. Now you should know the value of phase voltage in these converters. So it is root 2 Vs by 3 square by R in 180 degree inverter. Correct? How much we will get? We will get 2 Vs square upon 3R. That will be the 180 degree power. If we calculate power across 120, again same formula we will apply, and in 120 degree the phase voltage is Vs upon root 6. Okay, you need to practice the formulas. Then what you will get? You will get Vs square by 2R. Correct? Now when you will divide 180 to 120, then you might be getting 2 Vs square upon 3R divided by Vs square upon 2R, and when you will solve it, you are going to get 4 by 3 or 1.44. Okay, whatever is the values given does not matter, this ratio will always be 1.44. Correct? This ratio will always be 1.44. So remember this question. If suppose you will be given the power in 120, then what is going to be the power is 180, you can just multiply that power with 1.44 and you will get it answer. If suppose 180 power is given, 120 is to be calculated, divide that power with 1.44, you will get your answer. In that case, you need not to remember that many formulas. Okay? So if one power is given, another is calculated, if you remember this ratio, you can easily get it done. I hope that it is clear. Right? I hope that it is clear. No need to have all those data. It is very important. Right? Then moving towards the next question. Now see this one. A three-phase voltage source inverter as shown in the figure is feeding a delta connected load. Whatever derivation you generally do in classes is for star connected load. We have been given delta connected load. So the star equivalent of the load will be, okay, so what is delta connected load? 50 plus J50 just divided by 3 and you will get the star connected load. So it will be 16.67 plus J 16.67 ohms, right? This is the first thing that you have to do. Load should be in star. If it is given in delta, divided by 3, right? It is fed from a 600 volt battery. So Vs is 600 volt and the mode is 120 degree inverter. The reactive power consumed by the load will be, we have to find reactive power consumed by the load. So it will be 3 V phase square upon X. For active power we will write R, for reactive power we will write X. Okay. Now what is the phase voltage? Just now we have written in the first question, Vs by root 6 for 120 degree divided by X. Okay. Now you have all the values. So it will become Vs square upon 2X and Vs is given 600 divided by 2 into X value is 16.67. When you will solve it, then you will get 10.79. Okay, 10.79, the unit will be kVAR, which is given in option number A. Okay. So what you have learned from this question, that whatever derivation, this Vs by root 6 you have derived by assuming a star connected load. If the load is given delta, convert it into star, then do the things. Okay. For active power, R is responsible, for reactive power, X is responsible. Got it? So why we have taken this question? Just to remind you that delta load needs to be converted into star load. Okay. For reactive power, X will be involved. Right? So I hope that this is also very easy question and it is clear to you as well. Right? Now moving towards the next question. Now it's a combination of chopper and inverter. A buck boost converter, what converter? Buck boost converter chopper operating at a duty ratio of 0.75. Duty ratio is 0.75. Providing input to the three-phase 180 degree inverter. Inverter type is 180 degree. inverter, voltage source inverter from a fixed DC voltage source of 110 volt. The DC voltage given to the chopper is 110 volt. Okay. The total power dissipated across the star connected load of inverter having 20 ohm resistance, R is 20 ohm per phase. What will be the three phase power is what we have to calculate, and it is like we have a BB converter, buck boost converter, giving power to a three phase inverter, and that is feeding to the load, right? Your time starts now. I hope that you can solve this question. A chopper is feeding to inverter, inverter is feeding to load. Finally, you have to calculate that what is the absorbed power across the load, right? What is the power absorbed across the load is what we have to calculate. Bindu is saying A. Yes, that's correct, Bindu. Very good. Very good. Okay, so we have this situation. Just see. First, we have buck boost converter. Okay, then we have inverter, and then we have the load. Right. So see, this is our buck boost converter. And input voltage to this converter is how much? Input voltage to this converter is 110 volt, right? It is operating at a duty ratio of 0.75. Then it is feeding to an inverter. So what is going to be the output voltage? Is going to be the input voltage to inverter, right? This is our three phase 180 degree inverter. Now this inverter is feeding to the load, right? So what is going to be the output voltage of this inverter is D over 1 minus D Vs, right? So 0.75 upon 0.25 into 110, so it will be 330 volt, correct? So this 330 volt, which is the output of this buck boost converter, okay, will become the input here. So input to this converter will be what? 330 volt, correct? Now what will be the output voltage, okay, of this converter? So if we calculate the phase voltage, this will become root 2 Vs over 3, because it is 120 degree inverter. So root 2 into Vs is how much? 330 upon 3, okay. So from here you will get the phase voltage, right? Then what is the load power? So power 3 phase, okay, I am not putting the values here, let me write it here. 3 V phase is square by R, okay, or 3 times V phase is root 2 Vs over 3 is square divided by R. Correct? Now what we will get? 2 Vs square by 3 R. Just put the values. So 2 Vs. How much is Vs? Vs here is 330 volt square by 3 into resistance is 20. So when you will solve it, you will get 3.63 kilowatt, which is in option number A. Correct? This is how you could have solved this question, and what Bindu has stated, A as the correct answer, is absolutely correct. Got it? So this is a very good question. It's a mixed concept question. Chopper is feeding to inverter, inverter is feeding to load. Finally, we have to calculate the power absorbed across the load. And one thing you might have seen, that phase voltage formula for 120 degree inverter and 180 degree inverter is very important. You can practice that formula very well. Okay, if you know that formula, power calculation will become very easy. Okay, so I hope that it is clear to everyone, right? Now just see this question. Okay, too much data is given. What we have to do here? A single phase voltage source inverter is feeding to an RL load, as we can see. It is controlled by sinusoidal pulse width modulation technique, and the reference and sinusoidal voltage and reference triangular voltage of 10 kilohertz frequency are shown. So we have reference and carrier voltage. We define something called as modulation index, which is reference upon carrier. How much is the reference voltage? 1. How much is the carrier voltage peak? Okay, this is peak to peak. So we will get modulation index as 0.5. Right? Now the reference value, the reference wave is given as VR equals to 1 sin 100 pi t, and R is 10 and XL is 12 ohm at 50 hertz. Then RMS value of fundamental component of current will be what? Guys, we have to calculate RMS value of fundamental component of current. Okay, RMS value of fundamental component of current will be equals to RMS value of fundamental component of voltage divided by fundamental impedance. Correct? So we can calculate fundamental impedance by doing R square plus XL square, and R is given 8, XL is given 12. Okay, so Z1, we will get Z1 which will be 14.42. Correct? Now what is fundamental RMS voltage? So just see, fundamental peak voltage is MAVS, modulation index times the source voltage, because it is full wave converter. If it is half wave converter, means half bridge rectifier, then we could have written MAVS by 2, right? So this is peak to peak voltage. If suppose I am calculating the RMS voltage, then I have to write MA Vs over root 2. Okay. Now MA is 0.5, right, and Vs, the source voltage, is 500 volt divided by root 2. Okay, divided by root 2, and you will get 176.8 volt as the voltage value. Then come here, 176.8 divided by the impedance is 14.42. When you will do that, you will get your answer as 12.26. Answer will be 12.26 ampere. That's it. Okay, the problem is done. Same problem may be repeated for half bridge inverter. Then only one change. You have to write here MAVS by 2. MAVS by 2, where Vs will be the VDC voltage. Okay. So in this way you can solve this question. Got it? I hope that it is clear, right? Modulation index. Right now gate authorities are very much interested in asking inverter questions which involves modulation index. Okay, so in this way it becomes a very important topic. So prepare all those formulas of modulation index, right? I hope it is clear, right? Then last question, and this question is a gate question which I have taken because I feel that it is very important and you may again get a question like this. Okay, so what is given here? A 3-phase grid connected voltage source converter with DC link voltage of 1000 volt. So we have been given Vs, which is 1000 volt, is switched using sinusoidal pulse width modulation technique if the grid phase current is 10 ampere, okay, output current is 10 ampere, and the 3-phase complex power is given minus 4000 to J 3000 volt ampere, then the modulation index will be, we have to calculate that what is going to be the modulation index, right? And we have been given the power S is given in this format, minus P minus JQ, and this is minus 4000 minus J 3000. So we can write that P is 4000, right, watts, and Q will be 3000 volt ampere reactive, correct? So these are the given values, right? These are the given values, and we have been given 3-phase converter. So in 3-phase converter we have to calculate what? We have to calculate modulation index, right? Now what is the required formula? So just see, peak to peak fundamental voltage is and line voltage, okay, this is root 3 MA Vs by 2, that is the formula, right? Peak to peak fundamental line voltage is root 3 MA Vs by 2, got it? So we need to calculate MA, we need to have the value of Vs that we have, we need to have fundamental line voltage, right? How we will get that? So you can see P is given, P equals root 3 VL IL and cos phi. So P is given, VL we need to calculate, IL is given, cos phi we don't have. So if we can calculate cos phi, the things will become easy, okay? So just see, S, P and Q are given, and you know that cos phi is P over S, okay? So from here P is 4000 and what will be S? So if P and Q are given, S will be P square plus Q square, 4000 square plus 3000 square. So from here you will get 0.8. Now come back and put the values. It is 4000, it is root 3, and VL we have to calculate, IL is given 10 and it is 0.8. So you will get the VL value from here. And how much is the VL? VL is 288.67 volt, okay? This is the line voltage, okay? And this will be the RMS value. Normal values are RMS values. So we need to get the peak value, okay? And basically this is fundamental voltage because fundamental component is responsible for power. So this is fundamental, okay, RMS component of line, which is 288.67. If I want to get the peak component, I need to multiply, okay, VRMS is Vm by root 2. So Vm will be under root 2 times the RMS value. So how much we will get? So we will be getting 408.24 volts. So you have calculated this voltage, right? Now just put the values here, just see. So from this formula, this value we have right now, which is 408.24. 408.24, this is equals to root 3 MA we want to calculate, Vs is 1000 by 2. So from here you can calculate MA, and MA is coming 0.47, correct? So in last question you have seen that we have used the formula for single phase full bridge inverter. Here we are using formula for a 3-phase converter involving modulation index. You need to practice this formula. Rest what we have done here is fundamental knowledge that you might have acquired from network as well. Okay, so this is all network and then this is power electronics. So you need to practice this formula. I just want to make you realize that these are the important formula, and that is why I have taken this particular question, although this is a gate question. Got it? So what is the peak to peak formula, fundamental voltage formula for 3-phase converter, for single phase full bridge converter, for half bridge converter? You need to practice that, right? This is the formula, Chetan. Peak to peak, right? This is peak to this is fundamental peak voltage in the line form is √3 MAVs by 2, correct? Now when you will do the calculation, you will get the line value, and that is fundamental voltage, because fundamental only is responsible for active power, and this is RMS value. You need to convert it into peak value. For that you have multiplied with √2 to convert it into peak value, then just put the formula and get MA calculated, right? So guys, this is what I wanted to share with you. All the questions are very good. I hope you might have enjoyed. Okay, so yesterday we have discussed electrical machine. We have solved very fantastic questions. Today we have solved some very good questions of power electronics. Now be ready. Next week I am coming with power system. Okay, you will be notified in our channel. So next week I am going to take a score booster session of power system. So in this way, electrical machine, power electronics we have already done. Now you will be able to do power system next week. So in this way, what will happen, all your core subjects will be covered. All your core subjects will be covered, right? So if you are new to our channel, subscribe our channel so that you will get a reminder. If you have not subscribed if you have not joined our Telegram channel, do join our Telegram channel so that you will get a regular update that what we are doing every week. Okay, and next week also I am going to take EMFT, gate score booster session of EMFT, one of the nightmare for all electrical and EC student. Come and join this gate score booster session. I will cover every important concept here so that you will get a revision and practice of some important question. And as I am telling you, join our Telegram channel so that you will be getting regular updates about everything. The link is given in the description box, and you will get the PDF of this class immediately once the class will be ended. Okay, and do not forget to join our test series plus. It is the right time to attempt the test and practice GQB questions which you are getting in this course, test series plus course, and on a discounted rate. Okay, and if you are very much impressed with the teaching and learning methodologies of IMS Gate Academy, you can join our live 26-27 program. Okay, you will get 800 plus hours of live interaction. You will get theory book, exercise book to practice many number of questions, GQB booklet, and you will also get some personalized mentorship session where you can strategize your preparation, right? So again, set a reminder. Next week I am going to cover EMFT and power system. Do not forget to join, right? So thank you so much for joining this session. I hope that you might have enjoyed this session, and this will help you in scoring maximum marks in upcoming GATE exam. Thank you so much.